We have an RC circuit as shown in the picture. The geometry of the capacitor is given and the EMF voltage is given. Now the capacitor is fully charged right now, and we'd like to calculate the charge accumulated in the capacitor at this time. The formula for the charge stored in the capacitor is V times C, the voltage across the capacitor's terminal, times the capacitance of our capacitor. I'm using labels I for initial, so these are all the initial values at the start of the problem, and our capacitor again is fully charged. Now the capacitance of the capacitor is not given, but the geometry is given. So that's going to be equal to, C is equal to epsilon 0 times plate area divided by the plate separation D. And the voltage across the terminals of the capacitor is equal to the EMF voltage because the capacitor is fully charged. Let's plug in the numbers and calculate the numerical value for the initial charge. After the numerical substitution, we get charge equals 1.33 times 10 to negative 11th coulomb, or 13.3 picocoulombs. Next, we insert some dielectric material in the capacitor with dielectric constant equal to 13. And we'd like to calculate the current passing through the circuit immediately after we inserted the dielectric material. To calculate the current, let's use Kirchhoff's loop rule. Starting from point A, going in the clockwise direction, we get plus EMF minus I times R minus the potential difference of the capacitor. Now note that this potential difference is different now that we have inserted the dielectric. The potential difference is no longer equal to the EMF, but there's a different potential difference across the terminals of the capacitor. So that's at the first moment, right after we have inserted the dielectric. Now, what is that new value of the potential difference? Again, I'm referring to V sub C final. I have calculations on the side for that. Now remember, V is equal to Q divided by C for the capacitor, right? Now the very first moment, the moment you insert the dielectric, the charge doesn't change yet, right? So the charge is the same. So we still have the initial charge, Q initial, but now the capacitance has changed because of the dielectric. So we have C final. So V sub C final is equal to Q initial divided by C final being the original value of capacitance C initial times the dielectric constant K, right? So V sub C final is equal to Q initial divided by K times C initial. And Q initial divided by C initial, well, that is the original initial voltage of the capacitor, which is the value it had before we inserted the dielectric, which is basically equal to the EMF. So really the final value or the value of the capacitor's voltage right after we have inserted the dielectric is equal to the EMF voltage divided by the dielectric constant K. Here I have rearranged my equation and isolated I and then plug in the numbers. We get I equals 0.738 amps. By the way, the reason V sub C has a negative sign in the Kirchhoff's loop equation is because as we're going clockwise, we go from the upper plate of the capacitor towards the lower plate, and the upper plate is the positively charged plate, right? Because it's on the same side as the positive terminal of the battery. So the upper plate is positively charged, and as we go in the clockwise direction, we go from the upper plate, positively charged plate, towards the negatively charged plate. That's a decrease in voltage. That's why we have a negative sign in front of V sub C final. Now we're calculating the potential energy stored in the capacitor immediately after the dielectric is inserted. Again, I'm using the label final for the moment right after the dielectric is inserted. So U sub C final, the potential energy final, is going to be equal to 1/2 C final times VC final squared. So the capacitance C final is the capacitance right after the dielectric is inserted, and V sub C final is the voltage across the terminals of the capacitor right after the dielectric is inserted. As we already mentioned or explained before, C final, the capacitance value is now the dielectric constant K times the initial capacitance value, so K times C initial, and the voltage across the terminals of the capacitor is equal to the initial value of the voltage divided by the dielectric constant K. And remember, that initial value was the EMF. So in the last line right here, I have replaced the initial value of the voltage with the EMF voltage. That's the voltage across the terminals of the capacitor right before we inserted the dielectric. And also for the capacitance, because the value is not given, we have epsilon 0 times the plate area divided by the plate separation. Now I have a factor of K in the numerator and a factor of K squared in the denominator. Those simplify, so I only get one factor of K in the denominator. In the next step, let's plug in the numbers and calculate the numerical value for the potential energy. After the numerical substitution, we get 6.13 times 10 to negative 12 joules, or 6.13 picojoules for the energy stored in the capacitor right after the electric was inserted. The next question is, by how much does the energy stored in the capacitor increase from this value after a long time has passed? Now, after a long time has passed, the capacitor's potential difference again becomes equal to the EMF voltage. So let's recalculate the potential energy for the new capacitance value and the EMF voltage as the capacitor's voltage value. Here I have set up my equation and I call this potential energy at infinity, so I use the label infinity to indicate that this is after a long time has passed. It's equal to 1/2 C final times EMF squared. When we plug in the numbers, we get 1035 times 10 to negative 12 joules, or 1035 picojoules. I'm keeping the same power of 10 for comparison with the energy right after the dielectric was inserted. So if you want to calculate the difference, you can just subtract the previous value from this final value. Next, we'd like to calculate the total energy delivered by the battery right after the electric was inserted all the way until a long time after, basically from time equals 0 to time equals infinity. Now, for that, we are going to integrate power over time, because power is variable, power changes with time, so we just take its integral with respect to time. And power for the battery is equal to the EMF times the current being the time dependent quantity here, so that's EMF times I as a function of t. And what is the formula for current? It's equal to its initial value, initial current I0, that's what we calculated all the way at the beginning of this problem, times exponential of negative t divided by RC being the time constant of this RC circuit. Now for the C values for the capacitance, we need to use the value of the capacitance after the dielectric was inserted, which is going to be equal to K times the initial value of the capacitance. So that's basically K times epsilon 0 times plate area divided by D. So in the next line, first let's take this integral, and then I'm going to substitute the formula for C final. Here's the result of the integral. The integral of exponential is basically itself, but we multiply by a factor of negative r times CF, and this expression here in parentheses is equal to 0 minus 1, so that's negative 1. That cancels the overall negative sign in front of the expression. When we substitute the numerical values, we get energy equals 1910 times 10 to negative 12 joules, Again, this is the energy delivered by the battery from the moment the dielectric was inserted until a long time afterwards. Finally, we're calculating the energy dissipated by the resistor for the same time interval, that is from t equals 0 to t goes to infinity. Again, we integrate power over time. Because this is a resistor, power is equal to Ri squared, again I being our time dependent variable. The integral is going to be very similar to the previous one, except that the exponential is now being squared, meaning the argument of the exponential gets a factor of 2. And instead of the EMF, we have EMF times I0, we have R times I0 squared. And here's the numerical result for energy dissipated at the resistor, 881 picojoules. Now, if we add the energy dissipated at the resistor plus the energy stored in the capacitor, that should add up to the energy delivered by the battery up to 2 significant figures.